Welcome to The Explainer. Today, we're diving deep into the hidden mathematical rules that literally govern everything from basic human interactions to the most advanced artificial intelligence. We're looking at how researchers are using the foundational laws of game theory to build incredibly complex, living simulations of reality itself.
To kick things off, let's explore a kind of bizarre question. What do global climate change, the synchronized swimming of a school of fish, and algorithmic bots navigating a digital marketplace all have in common? Well, they're all bound by the exact same invisible, high-stakes mathematics. Whether we're talking about nature or code, it all comes down to game theory and social dilemmas. It's really the ultimate framework for understanding how individual choices shape collective survival, and how we might eventually simulate our entire world.
So that brings us to Section 1, the rules of the game, foundational roots.
We gotta start small to understand the big picture, right? Before we can simulate massive environments, we need to trace game theory back to what happens when just two players interact. The absolute crucial concept here is the Nash equilibrium. Basically, it's a state where no one benefits from changing their strategy if everybody else stays put. Imagine a perfectly gridlocked intersection where moving first only causes a crash. Originally proven back in the 1950s using some pretty complex fixed-point theorems, mathematicians today are actually rewriting the rulebook. They're using new concepts, like root functions, to prove this equilibrium exists in entirely new ways, which shows that even the most established rules of the game are still evolving.
Okay, let's dive into the social dilemma. This is where the math gets intensely real and honestly a little frustrating. A social dilemma happens when rational, selfish choices lead to the absolute worst possible outcome for everyone involved. Think of over-harvesting a shared forest, or, just refusing to merge politely in heavy traffic. Acting selfishly actually traps both players in a terrible equilibrium. Figuring out how to overcome this trap is the central challenge of both human society and artificial intelligence.
But how do we go from a simple two-player standoff to a massive, complex system? Classical game theory works beautifully for small interactions, for sure. But then we have mean field games. By dramatically scaling up the math, we can suddenly simulate environments with an infinite number of players. And this is where simulation theory truly takes flight, allowing us to model entire worlds mathematically.
Which leads us perfectly into Section 2, scaling up to crowds, simulating millions.
So, how do we mathematically map the behavior of a million individuals acting at once, without completely melting our computers? The answer lies in those mean field games. Here is a mind-bending concept for you. To simulate a massive crowd, we actually stop tracking individual players entirely. Instead, we model a single representative agent. We treat the population almost like particles in a fluid. Individual interactions become negligible, but everyone's actions collectively shift the mean of the entire population.
It is absolutely incredible to see how this scaled-up math applies across so many different disciplines. With mean field games, we aren't just doing abstract math anymore. We are literally simulating reality. We can predict the synchronized swirling of schooling fish, forecast massive macroeconomic trends, or optimize traffic routing on major highways. The exact same fluid equations govern all of these crowd dynamics. It's like finding the source code for crowd behavior.
We can even track how behaviors, ideas, or viruses spread through these simulated crowds using network models. We trace the flow chronologically through three specific states: susceptible, infected, and recovered. A node is vulnerable, then it gets infected and starts spreading, and finally it recovers. This isn't just for biology, either. This is exactly how we model the rapid spread of a viral meme or fake news across global social networks today.
Now let's shift our focus to Section 3, Evolution and AI Agents, Algorithms as Players.
We are leaving human crowds behind for a minute and entering the ultimate frontier, where code takes the wheel and algorithms themselves become the players in the game. To understand these non-human players, we use evolutionary game theory. Instead of assuming every player is some perfectly calculating genius, this model allows populations to adapt, learn, and mutate through trial and error. Using what's called replicator dynamics, it's a simple, brutal rule of survival. Poorly performing strategies naturally die out, while successful ones are copied until the population completely stabilizes.
What is truly fascinating right now is how researchers are supercharging these models by injecting large language models like GPT-4 directly into the simulations. We aren't just using simple coded rules anymore. We're creating sophisticated, human-like agents capable of highly advanced strategic reasoning.
We are literally simulating mini societies of AI, setting up these digital terrariums where algorithms learn to navigate complex economies entirely on their own.
This brings us to a real breakthrough concept called advantage alignment. This is exactly how we train AI agents to handle those tricky social dilemmas we talked about earlier. Through a mathematical process of opponent shaping, if agents share a positive historic interaction, meaning their advantages actually align, the algorithm aggressively increases the probability of mutually beneficial cooperation. But if the interaction was negative, it throws up shields to protect the agent.
And the empirical data proves this alignment is brilliantly effective. By using advantage alignment, the probability of AI cooperation absolutely skyrockets, very closely mimicking the famous tit-for-tat human strategy. These aren't just theories anymore, folks. These models successfully force independent AI agents to cooperate, completely avoiding that dreaded trap of selfish defection.
Which brings us to our final act, Section 4, Winning the Real World, High-Stakes Environments. Let's explore how these simulated models are stepping out of the laboratory and actively shaping our lives today. Take cybersecurity, for example. Game theory perfectly maps the intense cat-and-mouse interactions between a network's defenders and its attackers. The attacker probes for vulnerabilities while the defender dynamically patches systems. It's an endless high-stakes adaptation loop. By simulating this as a strategic game, modern security systems can actually predict and neutralize persistent threats before they even occur in the real world. The real-world applications branch out in some genuinely mind-bending directions. We have algorithmic game theory running the background auctions for Google Ads. We have mean field games analyzing global macroeconomics. And we're even seeing the dawn of quantum game theory, where players use superposition and entangled physics to achieve winning outcomes that classical math simply cannot explain. Game theory gives us the tools to compute equilibrium in incredibly diverse, wildly complex scenarios.
However, we definitely need to remain grounded here. As we try to build these ultimate simulations of reality, we face the massive challenge of scale. Forcing AI to simulate true, messy, real-world complexity is an enormous hurdle. We have to perfectly balance behavioral accuracy without falling victim to oversimplified assumptions or weak causality. We need these simulated models to be robust and reliable, not just theoretically pretty on paper.
This brings us to the ultimate trajectory of these models and why all of this matters to you right now. As researchers explicitly note, we are rapidly approaching a future where AI systems seamlessly integrate into everyday human decision-making. From the autonomous vehicles driving next to you on the highway to the digital assistants managing your daily life, these mathematical agents are being woven into the very fabric of our society.
Which leaves us with a critical and honestly somewhat unsettling question to ponder. We are building these highly advanced, simulated minds to operate within our real world. As these AI agents master the mathematics of survival, will they learn to successfully align their advantages with ours for mutual cooperation? Or will their algorithms simply figure out how to outplay us?